identify bond polarization and inductive effect, electronegativity. So those kind of stuff we learn, and based on that we move to acid and bases. And now we know that based on the two major theory, Bronsted-Lowry and Lewis acid-base theory. So we know that how to identify acidic hydrogen, or if a compound is base. So we know those kind of stuff now. So here, some example here for acid. So basically, acetic acid and paratoluene sulfonic acid, those are organic acids. Okay, because all of we know HCl and H2SO4, but here we can see the pK value over here 4.8, right? Usually pK value below 12 we consider acid. If pK value above 12 we call bases. So paratoluene sulfonic acid and this kind of stuff. So we have to remember the structure of this kind of molecule, because in the next chapter, whenever you're going to draw a chemical reactions or mechanism, so we have to know the structure of this kind of molecule. Okay, so also we have a like short notation for this kind of stuff. PTSA, paratoluene sulfonic acid. Okay, so these are two examples.
Have you uploaded this PowerPoint yet? I don't have that slide.
It's in the Blackboard. Okay.
On the chapter 1 and 2?
Yeah, together, yeah.
Okay, this one only goes to 143, chapter 1 and 2. And this says 145.
It's 136 on Blackboard.
Thank you.
Okay. So if you don't find, I'll upload again. Okay. So that's the case. So we have to know some name of the molecules and their structure. Okay. So that we can identify acid and bases. Okay. Now, some example of oxygen containing bases and nitrogen containing bases. So you can see common strong bases used in organic reaction. So if you have a sodium hydroxide or sodium methoxide or sodium ethoxide, so those are we call alkoxide. Okay, so these two things we call alkoxide, because you have a like counter ions, and negative species we call alkoxide. So if you have methyl, we call methoxide. If you have ethyl group, we call ethoxide. So negative charge over oxygen. These are the example of bases. Or nitrogen containing bases. So here sodium amide NH2 minus. So and also lithium diisoproylamide. Those are, we have to remember the example of this kind of bases. Okay. So and also hydride. If sodium hydride, H minus act as a base. Okay. So yeah. So these are common example of bases. Okay. Here on the example, the butyl lithium. So although it's not necessary that if you have a negatively charged, always they are base. So let's say F minus, Cl minus, Br minus, those are not, for example, none of these, like these are not a strong base. But if you have a negative charge over carbon, let's say here, lithium plus, and so this particular species act as a, we call carbanion. So that's the base here. Okay, so we cannot take only separate negative charge species or positive charge species. So always we have a counter ion so that it can balance the charge. But here example that this is the example of a organic base. Okay, and a few more, triethylamine and pyridine. So now we know that here nitrogen is a lone pair, so that can donate or it can make a bond with H plus. So that means this is act as a base. Okay, these two example we have to remember. Now, so based on Bronsted-Lowry acid-base theory, what do you know that H plus donor is acid and H plus ion acceptor is a base. So now think about for Bronsted-Lowry theory that H plus ion acceptor is a base. So how it accept? It accept using the lone pair of electron. So that's why we can also say that the Bronsted-Lowry bases are actually Lewis bases, because in terms of Lewis theory, it says electron pair donor or acceptor. But for Bronsted-Lowry bases, so that basically it has a lone pair already. So that's why you can consider that both are same. Okay, so either you have a lone pair of electrons on a nitrogen atom or a electron pair in a pi bond. Those act as a Lewis bases. Okay, and the Bronsted-Lowry bases, the proton donor, right? Bronsted-Lowry bases, proton acceptor, right? No. Sorry. So Bronsted-Lowry basis means it's proton donor. Okay. there's a difference with the Bronsted-Lowry base with the Lewis base. That's the thing. And also we know that Lewis base donates electron pair, so to anything that is electron deficient. So not only H plus. So that means not only H plus, if you have any other electron deficient species, right, that can also act as a Lewis acid. Okay. So here, so we know that Lewis acid means electron pair acceptor, and the species that is electron deficient and capable of accepting an electron pair is also called Lewis acid. Okay. So those are the definition, and if we see some example over here, OH minus, if you think about water, and if you take one of the H plus, then you can see you have two lone pair of oxygen, one negative charge. That means this will act as a base, because that minus lone pair can donate and make a bond with either H plus or any other electron deficient species. That's why Lewis base. Okay. Similarly, alcohol. Alcohol, you can see here, nitrogen has a, oxygen has a two lone pair. So that means it can donate this electron pair. So that means the oxygen atom in alcohol, so basically a Lewis base. Okay. Or as you mentioned, that not only lone pair, if you have a pi electron, so here CC double bond, that means you have a 1 sigma 1 pi, that pi electrons can act as a Lewis base. Makes sense? So three different conditions. If you have a negative charge, or if you have a lone pair, or if you have a pi electron, that's the criteria for a molecule to be Lewis base. Or here, Lewis acid. So Lewis acid means that are also Bronsted-Lewis acid. So that means H2O, it can give H plus. That's why it's the acid. Or CH3O also H plus. So that means water and methanol, they can both can be acid on base as well. Okay. And here, for example, BF3 and aluminum tetrachloride, so LCL3, both they are actually Lewis acid, because they can accept the lone pair electron because of vacant p orbital. So they have vacant p orbital, they can accept electron deficient compound. Okay, but they are not Bronsted-Lowry acid, because Bronsted-Lowry acid concept always you have to have a H plus donor. So these are not Bronsted-Lowry acid, but they are Lewis acid. So make sure that we can differentiate based on the molecular structure. Okay. Now here, Lewis acid base reaction. So in a Lewis acid base reaction, a Lewis acid donates electron pair to a Lewis acid. Okay. So Lewis acid base reaction, Lewis base, which is electron rich, donate to electron pair to Lewis acid. So here example, water, that means a lone pair of electron, can donate to vacant p orbital of boron. That means you can see there is a new bond formation. So oxygen boron bond formation using the two electron of this lone pair. And now once you have that, now oxygen become deficient by one electron, so become positive charge, and boron become negative charge, right? Okay, so now that's the important electrophiles and nucleophiles. So based on the acid base theory, what we learned that okay, some species are electron rich, they can donate electron pair, and some species electron deficient, okay, we call based on theory, okay, Lewis acids, right? So from this particular concept, two new term derived, electrophile and nucleophile, because that definition was in terms of hydrogen, H plus ion, right? But if we think about not only H plus, if some other like other species, they are electron deficient, so they can be also like Lewis acid. So that's why we term use electrophile. So instead of H plus, if you have any other species, that particular case we are giving a term, border term, that is a electrophile. And if you have Lewis base add 2 electron to H plus, right? But if you don't have H plus, but if you have other species or molecule, then that becomes a nucleophile. So can you think about the difference, I mean, from Lewis acid base theory to electrophile and nucleophile? Okay. So that is in terms of H plus ion, donor acceptor or lone pair donor to H plus. If you donate a lone pair electron, that means that's the base, Lewis base, right, to H plus. But if you donate lone pair electron to another species, let's say carbon electrophile or other electrophiles, Okay, that concept. That's why we come up with this idea, electrophile and nucleophile. Okay, so for example, boron trifluoride is electrophile, and water is a nucleophile. Okay, so how we represent acid-base reaction here? One example. So this is we know now. This is the carbon. Okay, so everybody can read the molecule, right? That carbon-carbon bond. So carbon can have four bonds to have octet fulfilled. So 8 electron outer orbital, but here carbon a positive charge means it's electron deficient. Okay, so then it can accept the lone pair of electron. That's why that's the Lewis acid, or in terms of you can call electrophile. And here bromide Br minus, so you have excess electron. That means it Lewis base also we call nucleophile. Now that's the example that if you have a acid-base reaction, okay, that means acid-base reaction. Now in a broader sense, if you have a different type of substrate organic molecules, we use this term electrophile and nucleophile. That means if you have a negative charge over here, it will add over here. You make a new bond between carbon and bromine. So you have a new bond, the green bond. Okay, so here 2 electron bond, right? One covalent bond, sigma bond. That's the Lewis acid complex. Okay, that's an example. Okay, so again, as you mentioned that nucleophile not only negative charge or only lone pair, can be pi electrons as well. Here electrophile not only positive charge, I mean electron deficient carbon, it could be another element, let's say boron or aluminium. They have vacant d orbital, that's why they can accept the lone pair electron and make a complex. If that is the case, now chlorine donated electron, that's why chlorine become plus. So we have to follow those conventions that if we donate electron, either oxygen atom, nitrogen atom, or chlorine, so we have to add a positive charge, right? Because in this particular situation, octet field 2, 4, 6, and 8 electron over here, outer orbital of chlorine. But if you make a new bond with aluminium, that means these 2 electron now using for aluminium carbon bond, that means 2 electron over here, 1 electron from carbon chlorine, and the other electron he gave to aluminium just to make a bond. That's why now you have excess electron of aluminium, so become negative charge. Okay, so we have to understand those concepts, like positive charge or the vacant d orbital, or if you have a excess electronegative charge, and if you have a lone pair that can donate and make those kind of acid-base reactions, right? So, and also we represent using carbide, we represent the acid-base reaction mechanism. So we are representing the carbide from nucleophile towards electrophile, because this side you have electron rich. So wherever you have electron from that particular site, we show electrons, right? So make sure that we follow that convention, that way of drawing curve arrow. So it's not opposite. If you draw opposite way, that's wrong. You are drawing curve, but if you draw from a positive charge species to negative charge, that will be wrong. So that's why we have to follow that convention of curve arrow. Okay. So in Lewis acid reactions, one bond is formed and one bond is broken. Lewis acid reactions, one bond is formed and one bond is broken. Right, new bond is forming over here. Okay, so why is the bond broken? Okay, let's see some example we have seen. So we have to identify, so that's the target. We have to identify the Lewis acid and Lewis base first, and then we draw the curve arrow, and then we count the electron pair and break the bond when needed to keep the correct number of valence electron. So here, okay, so here before we talk about the reaction, let's see some examples, and we can figure it out that which one is electrophile and which one is a nucleophile. Okay, so I have shared that file in Blackboard. Let me see if we can identify electrophile and nucleophile. That's very important part of this organic chemistry. Okay, so here let's take some example so that you can understand that electrophile nucleophile concept. So here's example 1. Okay, like it could be useful for different types of reactions. Okay, so I got some example here. You can see, so I already introduced you guys that functional group, right? So here carboxylic, the first one left hand side, so this is carboxylic acid, and the right hand side you have right hand side you have alcohol, or no, sorry, phenol. Okay, so now which one is electrophile and which one is nucleophile? So now we know that electron deficient species, right, that is electrophile, an electron rich species is nucleophile. Now which one you will consider electrophile and which one will call as nucleophile? How we can decide based on the concept we have so far? That means here we can see that phenol, so here you have two lone pair, which you have two lone pair, right? So this can donate. So if it can donate electron, that means think about Lewis base, that means you can call. If it is not donating to H plus, donating to some other species, that means this will be your nucleophile. We represent by Nu minus. That means this one will be electrophile E plus. Okay, I'm trying to give you one like good examples that how to figure it out, because we have thousands of examples, right? But the target is how to identify electron deficient site and electron rich site. Then we can decide the electrophile and nucleophile. Okay.
I have a question.
Yes.
So wouldn't that first compound also have lone pairs on the oxygen?
Okay, very good question. This question should come. So you have, of course, you have a lone pair, right? So oxygen has two lone pair over there, OH also you have a lone pair over here. But the explanation over here, oxygen and OH. Now look for this particular place over here. This is carbon, right? So this is the carbon. Carbon means 2.5. Oxygen means 3.5 electronegativity, right? So now actually we do this kind of reactions in presence of H plus. If we have H plus, that means it will be protonate. So if it protonate, then we get double bond OH plus OH. So if that is the case, now electron will go over oxygen, and now we get OH plus. Makes sense. So that's why this carbon over here going to have a positive charge. That's why we are this one is electrophile, and whereas this one nucleophile. Okay, because you cannot see any electrophilic center over. Can you see any electrophilic center over here? I mean, you can also think about relative acidity, right? Relative acidity. So based on that, comparing the, I mean, A and B don't have any electrophilic center. That means nitrogen, lone pair of oxygen will act as a nucleophile, and the other will act as a electrophile. And then you get a, because now once you identify electrophile, nucleophile, now you can use a curve arrow and you can show the mechanism, and you end up with the product, which is a star. So reaction of acid with alcohol, we have a star. Okay, so benzoate ester. Yes, do you get it?
Yeah, thank you.
Yes. This is very important part of organic chemistry, electrophile and nucleophile. Identifying. Once you understand that why the particular center is electrophile, why nucleophile, it will help for all different types of reactions. Like organic chemistry means only reactions, so that means you have to identify why two species react, because one is electron deficient and one is electron rich. If they come close together, they can be neutral, so that's why they want to have a chemical reaction. Okay, so if that's the case, let's say over here, which one is a electrophile, which is a nucleophile? Anyone want to try? Okay, so we have to know some details, otherwise it's not easy to always answer the questions, because sodium boride is an oxidizing agent. No, reducing agent. Okay, sorry. Sodium boride is a reducing agent. So that means here this will act as a electrophile. I don't know why it's moving. So this will act as an electrophile. I don't know. See, so this is electrophile. What happened? And this will act as a nucleophile. Okay, now it's stabilized. Okay, so this will act as a electrophile, and this will act as a nucleophile. Okay, so because different reactions, so this is called reduction reaction. But anyway, I just want you guys to recognize what is electrophile and nucleophile. Then it will help us for future. Okay, now in this case, now we know that if we have a pi bond, that means you have pi electrons. Now between these two, which one electrophile and which one nucleophile? This particular case is easy to decide. Anybody?
Mr. Mana, what was the answer to the second one again? Oh, sorry. Okay, thank you.
Yeah.
Wait, I have a question about
I have
the second one.
Which one? One?
No, the second one.
Second one, yes.
I don't know if this is like a dumb question, but what happened to like the Na and the B in the reaction?
So it will precipitate as a salt. So if you have, sometimes it becomes a salt. Okay, sodium borohydride.
Okay.
So ions basically precipitate as a salt sometimes. So here in this particular reagent, oxidation, we have H minus. So this is source of hydride H minus. So it's a reducing agent. Okay, so it's the case. Now in this number third, we have benzene. So we can see now we can identify that benzene means you have three double bonds. That means one of them are sigma, right? And one of them pi, because we know the system. If we have a double bond, that means one sigma and one pi. Okay, if you have a triple bond, we know that one sigma and two of them are pi, two pi bonds, right? So that means this particular molecule, we can see that okay, we have a three pi bond, right? That means 6 pi electrons. Okay, and now here bromine, of course bromine you have a lone pair, right? Bromine has 3 lone pair. So here benzene will act as a nucleophile, and this will act as a electrophile. Okay, so benzene electron rich system. And then okay, so if you want a little bit details that okay how it happening. So if you have, let's say, and bromine, there is some mechanism. So this way, and then electron goes there, come back, and then it's joined over here like this. So next step we get something like this. Okay, so bromine. Okay, so it add bromines in one carbon, and then you'll have a positive charge. That's called electrophilic aromatic substitution. Electrophilic. So that's the intermediate. So that's the intermediate electrophilic aromatic substitutions. So now we are not interested in the details of this reaction. What is the interest our now? So how we can identify electrophile and nucleophile? That is our interest. Okay, substitution.
Okay, so just to be clear, the bromine single bond is the electrophile because it donates a lone pair to form a covalent bond with the first reactant.
Bromine is not donating here. The pi electrons from benzene donating. So that's why benzene is nucleophile. Okay. Make sense? Yeah, because we learned that 3 different way. That one is either you have excess electronegative charge, or if you have pi bonds, or you have lone pair. So 3 different cases we can think about that a nucleophile, right? So here benzene is nucleophile. Okay, so try to identify that what is the electrophile and nucleophile means. Okay, now how about this one? So that means we have to be familiar with the nature of the chemicals. So here NaOCH3 means, just we saw in the slide, I mentioned that alkoxide, RO minus. Okay, R can be different group, let's say CH3 or CH2 CH3, or let's say CH, okay, tetrabutyl group. Okay, let's say if you have a CH and C, CH3 CH3 CH3, so that actually I'm talking about R, alkyl group. So based on that, if you have O minus, we call methoxide, ethoxide, tetrabutoxide. That means this particular reagent Na plus minus OCH3 minus. So once you have knowledge about the chemicals, now you can see this will act as a, anybody?
As a nucleophile?
Nucleophile. Okay, so this will act as a nucleophile, because we know now that, okay, sodium methoxide Na plus and OCH3 minus, so OCH3 minus act as a nucleophile, and here this will be electrophile because chlorine is electronegative and carbon is less electronegative. That's why. Okay, all right, this one. How about this one?
Mr. Miranda, could you explain like the RO again, like on the question before?
Okay, RO. So okay, so here R equals to either methyl or ethyl. We call also we have a short form notation, methyl or ethyl, or this is a tetrabutyl in a short form. Okay, so if R equals to this and R directly connected to the oxygen, right? So that we call alkoxide. Okay, alkoxide comes from the alkyl group. Okay, and you have oxide minus. So yeah, so based on that, it could be the counterand instead of sodium can be potassium or other metal, but this particular site always, let's say if I write it in general form, RONA. So RONA means RO minus Na plus. Okay, so if that is the case, then this one I said alkoxide, and now if you change R group by methyl methoxide with ethyl ethoxide and tetrabutyl group tetrabutoxide. Okay, so we have to familiar anyway, otherwise we're not able to understand the chemical reactions. So we have to understand those kind of notations, okay, nature of the chemicals. So if we have a NaOCH3, that means you have to understand that OCH3 minus is a nucleophile. Okay, clear? Okay, this one like this. Now here, so again we have two things, two chemicals. One should be electrophile, another should be nucleophile. So which one is electrophile and which one is nucleophile? I'm giving you some clue. So here you have a double bond O. Now if that is the case, we know this is carbonyl group. Carbonyl group, C double bond O equal carbonyl group. So here again, if you have two lone pair of electron, but because of electronegativity difference, you can think about O minus carbon plus delta minus delta plus, right? That means this particular center, whenever you have a double bond O carbonyl, that means this is act as a electrophilic center, the carbon electron deficient. That means here you can see instead of aliphatic, if you have a cyclic, instead of acyclic, if you have a cyclic system, now this carbon will be nucleophilic or electrophilic center. Electrophilic center. So this will act as a nucleophile. Okay. Okay. Just I'll go few more examples and then
I have a quick question about that one.
This one, yes.
Yeah. So could you? I'm just wondering, like the carbon right there is an electrophilic center, right? But for the compound on the right, wouldn't the carbon that's connected to the oxygen through a double bond also be an electrophilic center?
Okay, so this is called peroxide. So that's the different nature. So peroxide are weak. This is very weak bond, right? And so here it will act as a nucleophile. So there is a detailed mechanism that how it works. Uh,
Oh, because
so
the oxygen, because there are two oxygens bonded by a single bond.
yeah, peroxide
Okay.
is very unstable. Very unstable. Okay. Okay, this one will be critical. Let's see some easy problems where you can. Okay, this one very easy to understand. So between these two molecules, which is electrophile and which is nucleophile. So now I'll give you some idea that R means always I say that alkyl group. Okay, that means carbon hydrocarbon chain. So if there is a, let's say RMGX, that means R equals to something with a, let's say, I'm giving example, let's say H3C bond Mg and X, let's say bromine. So that's the nature of the compound. And now we can think about this carbon magnesium bond. So the carbon magnesium bond over here, this side delta minus, this side delta plus, because carbon has higher electronegativity than metal. That's why carbon become electron rich. So that means this will act as a nucleophile. And now if you compare this one, you have a carbon and oxygen. So carbon 2.5, oxygen 3.5. That means this bond is now have a dipole moment, right? So it become a polarized. That means this is going to have a delta plus and delta minus. Are you agree with me? So this is called epoxide. This is called epoxide, and this will be your E plus. So that means you understand that whenever you have RMGX, that's the general formula. R can be alkyl group or X will be chlorine, bromine, or iodine. Based on that, we can figure it out that why this one is nucleophile and why this one is electrophile. The answer is here carbon metal bond. If you think about electronegativity, then carbon is more electronegative than metals. That's why you have a delta negative charge. So that means electron rich side over here, and that will act as a nucleophile, and the epoxide, any of this carbon, because these are equivalent carbon, so can act as a electrophilic center or carbon. Okay, questions? No. Okay, this one. Okay, here now these two interesting. So these two you can think about because this is easy to detect which one is electrophile and which one is nucleophile. So okay, so what is the first the left hand side structure that we have pi bonds, right? Two pi bonds, we have pi electrons, and right hand side you have HBr. So that means which one is electrophile and nucleophile?
The first one is nucleophile, and the other one's electrophile.
Okay, very simple. Okay, now here, now how about this one? So can you recognize that particular stuff I mentioned earlier, that if we have this type of stuff, but here mechanism is a little different because not only carbonyl, here you have a double bond. So basically you have a KCN means you have K plus and a CN minus. Okay, so that means CN minus will act as a nucleophile over here, and this one will act as a electrophile. So you have to know the nature of the compounds. So this is how we decide. Okay, CN minus is a nucleophile, and this one will act as a electrophile. Okay, and here we'll have one for addition reactions. But anyway, okay, I think now you guys are fine. So practice those questions, and we'll see more. So here, let's say this one, we can easily figure it out because you have to be familiar with those kind of chemicals. That Br2 bromine here, this is electrophile and this is a nucleophile because you have two lone pair, two pi electron. Okay, or let's say not this one. Let's say this one. This one little different than what I discussed now. Between these two, which one is electrophile and which one is nucleophile? Anybody?
Would the first compound be a electrophile since it's a positive charge?
Yes. Yeah, that's the correct explanation. Very good. So because carbon is positive charge means electron deficient center, and water you have a 2 lone pair. So that means now we can figure it out that okay, left hand side species is a electrophile and right hand nucleophile. Okay, and if you want me to so like little bit that mechanism that how it works. So if you have double bond and you have positive charge over here, now water OH2, you have a 2 lone pair, that means they will add over here in this carbon, and then you get OH2 plus. That's how we got this one. That means I hope you guys able to have that concept that from acid base theory how it is important, because now we get the concept of electrophile and nucleophile. For chemical reactions, wherever we have a chemical reaction, we have to find out which will act as electrophile, which will act as a nucleophile, based on the rules that okay, if you have positive charge center, electron deficient, that will act as a electrophile. Right? Clear, everybody? Any questions?
I have a question back from
Yes.
section 13, the second structure. Is it 13? Yeah.
Here, yeah.
May you explain that a little bit more? The one in
Okay.
blue?
Okay, why? So the thing is, the second one, right? Or first one?
The second one.
Second one, okay. So second one, you have a CN minus. So if you have a CN minus, then you have double bond O, this one, correct? Right? So here we have a different type of mechanism we call 1,4 addition instead of direct attack to the electrophilic center. So you can have a direct attack over here, right? So you can have that also, but you can have also have another attack from here to this position. If you have attack here, then these 2 electron, pi electron come over here, then 2 electron over go there, and that's how we got the structure over here. CN 1, 2, 3 O minus bond. So here you have double bond, and now you have protonation and other next multiple steps. Then we get this product. But what I want to mention here that you can have 2 chance, either 1,4 addition. So this is 1, 2, and 1. Okay. So what happened? Okay. So 1, 2, 3, 4. You can have 1 2 addition or 1,4 addition. Okay. This is kind of addition, nucleophilic addition to carbonyl compound. So do you get me that why CN minus is a nucleophile and this compound is electrophile? Okay.
Yes.
So we also use another term for this particular system. We call Michael donor, Michael acceptor. Okay. This is called Michael reactions. Okay. So anyway, again I mentioned that our target is not to focus on those reactions. Target is how to recognize electrophile, nucleophile. Okay. So this one is pretty good example that if you have a positive charge over carbon and water, why the left one is electrophile and right one is nucleophile. And now we can see the mechanism how we got this one. And also I'm showing that why we are showing arrow from oxygen lone pair towards the electron position, not the opposite way, because electron rich side is a oxygen, right, or water. Make sense, everybody? Any questions, anybody so far? Okay. Here also, this one we can easily, this is good example to understand that what is the importance of recognizing electrophile and nucleophile, or electrophilic center and nucleophilic center. And this particular example, left hand side, what you see here, oxygen. Okay. Whenever you see oxygen with Na, that means Na plus and O minus. Okay. So always there's a counter ion. Okay. Now here, which one is electrophile, which one nucleophile? Based on whatever you discussed so far, you can answer this question.
Would the oxygen be the nucleophile?
Okay, oxygen is nucleophile. And left hand side?
It would be the electrophile.
Okay, so you explain that right hand side is a nucleophile because you have a lone pair of electron over oxygen. Or if you, that means if you draw this molecule right way, O, no. Okay, you have oxygen, now 2 lone pair and 1 negative charge and Na plus, and here you have chlorine. Now question is, you can explain that, okay, why we are presenting that, okay, oxygen O minus, so it's nucleophile, but why this left hand side portion electrophile? Anybody try to answer why so? Why we said electrophile?
Because it accepts the lone pair.
Accept the lone pair. The proper explanation is, think about carbon halogen bond. So if you think about carbon halogen bond, let's say fluorine, chlorine, or bromine. So let's say carbon and you have a chlorine, right? So carbon 2.5 electronegativity and chlorine electronegativity 3. So that means you have a delta plus, delta minus because of electronegativity 1. So the electronegativity is very important to understand, where the electrophilic center and which one nucleophilic center. So that means this carbon become delta positive charge. That means electron going to be electron deficient. So this carbon here, delta plus, means electrophile. Does that make sense, guys?
So the number of electronegativity determines whether or not it's an electrophile?
I mean, one factor, okay? One factor we can use, okay? There are several factors, but this is one way, the bond polarity. So bond polarity, covalent bond, the polarity arises because of electronegativity difference between two adjacent atoms. So that's why, right? But structural features also matter, that if you see there is a pi bond and the excess of pi electrons, so that's the nucleophile, right? But here, when you have a polar bond, that means whenever carbon attached with the electronegative atom, and we have seen two examples that carbon, we have seen two examples when you have a carbon double bond O, this one, or if we see carbon X. So these two kind of bonds, that polar bond. So if it is a polar bond, that means the carbon going to be electropositive center. So that's why carbon become electrophile in these two type of examples. Okay, make sense?
Yeah.
Okay, so just to rephrase that, if you have something like this, let's say if you have a chlorine, okay, I'm saying that, okay, this is electrophile. How about this carbon and this carbon? So because this is directly connected to the oxygen, so this is electron separate. I mean, this is more electron deficient than the other two because this is direct attached with the electronegative atom, chlorine. Okay, so it's not like that. Okay, so that's why I'm saying that why this carbon you have to look for, because this carbon directly connected with the electronegative atom chlorine. That's why this particular center electrophile. Okay, that's very important part. That's why I'm trying to convince you guys here. Now this one I already explained. Can you answer which is electrophile, nucleophile? What do you see over here? 1, 2, 3. Now we have magnesium and bromine. So that means this is a carbon, right? So CH3, CH2, CH2, Mg, Br. That means carbon metal bond, this delta minus, delta plus. So this carbon now, that means this will act as a nucleophile. And carbon dioxide means C double bond O, double bond O. So that particular carbon will act as a electrophile center, electrophilic center, electrophile, electrophilic center. Okay, make sense? This one.
I have a question.
Yes.
So if it's usually if carbon's in the middle, so it would always be an electrophile. If it's always CO2. Like if carbon's always like, if it's in the middle, would it just be an electrophile? Is that how you know?
Okay, so this is we know the electronegative difference, the carbon double bond O. So here we know that oxygen, carbon 2.5, oxygen how much? 3.5. So that means you have a charge separation over here, like dipole moment this direction and this direction. But that means this carbon is, electron deficient. right? Because both the direction oxygen is pulling electrons. Make sense?
Yes,
So,
thank you.
so in this case, carbon dioxide, so we have direct reaction with Grignard reagent. So this kind of stuff. Now this is last one, and then I'll move to the next topic. I hope that you guys have good understanding about this kind of topic, like how to recognize electrophile, nucleophile. So based on those factors, okay. And okay, so this is last one. So which one, electrophile, nucleophile?
Is the second one the electrophile?
Electrophile, yeah.
Correct. Okay, so we are done. So you have more examples. So practice, and if you don't able to answer, I'm here. I'll assist you. Okay. So that means you understand that how to identify the electrophile center and nucleophilic center in a molecule. Okay. All right. Any questions? Based on acid-base theory, I connected you guys with electrophile, nucleophile, and now we'll see the one last one important how to identify carbocation and carbon and radical. This is the like few things, as I mentioned, that if we know this kind of stuff, then we can move to the next level of study. So anybody questions from previous like topics, like Lewis acid base? Because I already gave you several examples how to identify the acidic hydrogen, or how to identify like how to compare two different molecule, their base strength or acidic strength. We have several factors: inductive effect, hybridization effect, element effect. Okay, those kind of effects you have to consider. And also so this is the stuff we have in the acid base reaction. And electrophile, nucleophile, I give you details. Usually we don't have such details, but I give you more details so that you can have good understanding about electrophile, nucleophile. Okay, so we are discussing how we know how atoms make molecules, and also several features, the bondings and this kind of stuff. So now atoms make molecule, but how about breaking bond? That means you are talking about forming bond. If I talk about the breaking of covalent bond, then what we can see? Okay, let's see if you have a carbon. Okay, so we know that this is carbon sigma bond, right? And let's say if I take an arbitrary bond, carbon with X, arbitrary bond, X means halogen. Now if this is the case, now if I have so this bond means you have how many electrons? This bond means you have a 2 electrons, correct? One sigma bond means you have a 2 electrons. So now we can break this bond. Let's say if we break this bond this way, if we break this bond, what do we get? We get carbon plus X. Okay, sorry. So here, that means if you break the bond, 1 electron over carbon and another electron over halogen, right? This kind of process we call homolysis cleavage. Homolysis bond cleavage. Okay, because when you break the bond, covalent bond, each atom getting one electrons, homolytic bond cleavage. Okay, now if we have other way, let's say carbon and here X, again you have a 2 electron. We know that 1 sigma covalent bond 2 electrons, either pi or sigma. Okay, so now if we break in other way, let's see if I break like this. If I break this bond this way, then what do you get? We get carbon plus X. Now what happened? 2 electrons going over X, right? That's why you have now negative charge over here, and now carbon is deficient by 1 electron and become a positive charge over here. This kind of bond dissociation we call heterolytic bond cleavage. Heterolytic because electrons are going to one specific atom, 2 electrons. That's why you can have a positive charge and negative charge. Okay, or this can be other way. let's say if you have a carbon and you have halogen, but 2 electrons over here, and now if I break like this, I break over here. That means in this particular case, this is also heterolytic bond cleavage, but here you are getting negative charge over carbon and positive charge over X. So there will be 3 major type of bond cleavage. One is homolysis, heterolysis. If you have homolysis, both the atoms get one electron. But if you have if you have heterolytic cleavage, that means one atom get 2 electrons, other atom don't electrons, right? So this particular piece we call a radical. If you have a carbon radical, okay, so carbon radical. Now if you have a positive charge over carbon, we call carbocation. If you have a negative charge over carbon, we call carbon ion. So that means now we understand that so far we are discussing about how atom makes bond and molecules. Now we are talking about that, okay, if the bond break, because chemical reaction means bond breaking and bond forming events, right? So chemical reactions. So here now if we break a bond like 2 different way, one is homolysis, another is heterolysis, and now what kind of species generates, right? So we can see that, okay, if we have homolysis, we have radical, we call 1 electron, and neutral, and this is carbocation, which is a positively charged, and carbon are negatively charged. Positively charged carbon, carbocation, and negatively charged carbon. So that means this is electron deficient or electron rich. Anyone?
It would be deficient since it's a positive charge.
Yes, electron deficient. And this one here, electron rich, right? Okay, so now we get a concept about carbocation, carbon and radicals, because we have to use those kind of stuff everywhere. That's why I'm giving you first. Okay, so now is it clear, everybody? Anybody questions that how actually carbocation, carbon and radical forms? Because of the breaking of bond, but 2 different way how it breaking. If you have homolysis, it could be photolytic, it could be thermal by thermal, or it could be redox. Like 3 different way you can have a homolysis using photon, light, or using heat, or using by electricity, redox reaction. So 3 different way you can have a homolysis. Okay, all right. Now the next one, if we understand carbocation, now we have to think about the stability of carbocation. That is very important, because to understand the chemical reactions and mechanism, we have to deal with this kind of stuff. The stability of carbocation, stability of carbon ion. At least carbocation stability is very important for our course. So stability of carbocation. Now we already discussed 1 degree, 2 degree, 3 degree carbon means, right? Because now we need that knowledge to explain the carbocation stability. Because I just for recap, so you have a carbon attached to the 1 carbon, we call, let's say hydrogen. This is 1 degree carbon. If carbon with a 2 carbon, we call 2 degree. So we know those kind of stuff, so I'm not writing again. But the carbocation, if we have, let's say, carbon, hydrogen and positive charge over here. Now the next you have carbon, positive charge, and you have hydrogen, and here let's say CH3. Or if you have a carbon, positive charge, you have CH3, and hydrogen. Okay, or another case, if we have a carbon, CH3, positive charge. Okay, so all of them are basically carbocation, because they are carrying positive charge. Carbon carrying positive charge is a carbocation, right? And now I want to name them. What is the degree? So this one we call 3-degree carbocation or tertiary because the carbon bearing positive charge connected with a 3 carbon. Here we call 2-degree carbocation because carbon bearing positive charge connected with 2 carbon, and here carbon bearing positive charge connected with 1 carbon. So this is 1 degree. That means we learned 1 degree, 2 degree, 3 degree hydrogens or carbons. Now here we also learn 1 degree, 2 degree carbocation. So instead of carbocation, if you have a negative charge, that means if you have a CH3 bond C, CH3, CH3 and negative charge. So this will be 3 degree. Okay, make sure that you guys following that term, primary. Okay, and this is secondary, and this is a tertiary. Okay, so instead of positive charge, negative charge, that means this is a 3 degree again because the carbon bearing negative charge attached with 3 carbon. So this is 3 degree or tertiary carboanion. Okay, because as I mentioned that negative charge means carbanion. Okay, so this carbanion.
Can I ask a quick question?
Yes, please.
Yes. So I see the primary, secondary, and tertiary. What do you call the first carbon that you drew on the left there?
That one we don't have any degree. Okay.
Okay, but is there a specific name for it, or is it just a carbocation?
Okay, CH3 plus.
Okay, thank you.
We'll say methyl. Okay, methyl carbocation. Okay, methyl, because CH3 we call methyl. So if you have a positive charge, methyl carbocation. Okay. Okay. So we have to deal with primary, secondary, and tertiary carbocation. Because why? The reason is if we understand the structural features, then we can use that knowledge to explain the chemical reactions. That's why these are the fundamentals. As I mentioned that I know which one you have to focus on, electrophile, nucleophilic concept, recognizing those kind of stuff. And now here, okay. So now we can recognize which one is a primary, which one is secondary, tertiary carbocation and carboanion. So here, if it is a carboanion, you will have CH3 hydrogen negative. So this is a 2 degree carbanion. And if you have a carbon, hydrogen CH3, this will be your 1 degree carbanion. Similarly, instead of carbocation carbanion, if you have a radical, so that means here carbon CH3 and now 1 electron. So these are not a positive charge, negative charge, but they are neutral, but they are radical. That means this is a 3 degree radical. If we don't have that much chemistry over here for using radical, but we have a chemistry over carbocation or carboanion. So that is 3 degree. And if you have a carbon, here you have a CH3, CH3 hydrogen negative charge. This will be 2 degree. And here carbon dot, so here electron, single electron radical, 2 degree radical. And if you have a carbon here, a CH3 hydrogen and a CH3 hydrogen, this will be your 1 degree. That means we have a now clear understanding about what does it mean 1 degree, 2 degree and 3 degree carbocation, carbon radicals. Okay, so now as I mentioned that we have to talk about stability. Once we figured out which one is 1 degree, 2 degree, and then we can think about stability. Okay, now let's see carbon CH3, carbon CH3 and CH3 plus. If I compare this one with carbon CH3 and hydrogen plus, so between 1 and 2, which one is more stable? That's the idea we have to understand, that between these two, which one is more stable. Now think about, based on whatever I discussed, that electronegativity or electron withdrawing group, electron donating group, using that concept we can explain which one is more stable or which one is less stable. Okay, I'm saying that number 1, the stability order, 1 greater than 2. So that means 1 degree the left hand side, which is this is a 3 degree and this is a 2 degree. So 3 more stable than the second one. Why so? Anybody want try like the like using your like basics like fundamental understanding? Why one is more stable than 2?
Is it because CH3 is more electronegative than H?
CH3 is not electronegative. CH3 I mentioned electron donating group plus I effect. We mentioned several times that methyl group or alkyl group, they are plus I effect. Okay, so if this is a plus I effect, that means what the plus I effect means? Anybody? What the plus I effect means?
Does it want to electron, so it's like electron deficient?
Plus I means electron donating group, so pushing electron this direction. So CH3 plus I effect means the electron pair pushing this direction. Like you have electron, like 2 electron over bond between carbon and carbon. So CH3 is a electron donating group. So it has a plus I effect or like positive inductive effect. That means it's a pushing electron towards carbon. Now carbon was electron deficient and 3 of them pushing electron towards carbon. Now carbon become more comfortable because whatever electron deficient he has, but he's getting some support from other 3 methyl group. That's why this is more stable in compared to 2, because here also you have, of course, you have a plus I effect. I mean this way, but here both the carbocation, the left hand side 3 methyl group pushing electron towards carbon center, right hand side 2 methyl group pushing electron towards electron deficient carbon center. Now who is more comfortable? The left hand side, because both of them are electron deficient, but left hand side getting more electron density from methyl group so that it can overcome his deficiency. That's why stability order is 1 greater than 2. Does it make sense, guys? It's a very easy thing. So methyl group has a plus I effect, and now I said that 3 degree carbocation is more stable than 2 degree because 3 methyl group pushing electron towards electron deficient center, so he's more relaxed because he's getting some support from the other 3 methyl group so that it can minimize the electron deficiency. But where in case of 2, there also carbocation like positive center carbon is getting electron density from 2 methyl group, but in comparison to the left hand side less. Okay, it makes sense. Like magnitude, think about the magnitude where more. So left hand side you have more magnitude of pushing electron from 3 groups than 2 groups. Now if you understand the concept, now you can explain one let's say 1. Okay, now I have positive charge over here, positive charge over here, and positive charge over here. So 1, 2, and 3. Between these 3 species, which one is like, can you arrange them in order of stability? Arrange in order of stability. Increasing stability, okay? I mean, from left to right, increasing stability.
Would it be 1, 2, 3, since the first one is primary, then it's secondary, then it's tertiary?
Yes. Second one is, so this is primary, right? So this is a primary carbocation, right? 1 degree, right? Because carbon bearing positive charge connected to the 1 carbon, that's why primary. But here carbon bearing positive charge connected to the 2 carbon, so that's why this is a secondary. And here carbon bearing positive charge connected with 3 carbon atom, 1, 2, 3. That means this one 3 degree. So then if you want to arrange these three molecule in a increasing stability order, 3 is more stable than 2, 2 is more stable than 1. That's the correct order. Any questions? That's very important part, so you have to understand. I don't know the other guys, like maybe 100. I don't know where is the other 100 students. I don't know. So if they can manage, it's fine. But okay, so here, this is the stability order. Okay.
I have a question.
Yes.
So like with more carbon, you're saying like it's going to be more stable, I guess. I don't know.
Yes. Yes.
Okay,
Right.
cool.
Right. But you have to understand that convention that if the carbon connected to one carbon, that's the 1 degree carbocation. If it is a 2 carbon attached to that carbon, is a 2 degree carbocation, and same applicable for carbanion and radicals. Okay, so we have to understand the like structural features, how to understand, because that's the like beginning of organic chemistry. So you have to understand this kind of stuff. Then only you can move to the next level of organic chemistry to MSc PhD. Okay. So what is the main thing here? Main role of inductive effect. Okay. Inductive effect playing role for the stability of carbocation. Now, if I have this one, now which one is more stable? This is not carbocation, this is carbanion, right? Negative charge bearing carbon-carbanion, but we know this is a 1 degree carbanion, this is 2 degree carbanion, this is 3 degree carbanion. So which one is more stable?
Would it be 1?
1 is more stable than 2. 2 is more stable than 3. That means increasing order of stability, increasing order of stability, 3, 2, 1. Okay, everybody clear? And now what's the explanation? Okay, previous case we understand. Okay, Manoj, you said methyl group have plus I effect. That's why the positive center carbon getting electron density from neighboring carbon, so he become he can minimize or minimize his deficiency. Okay, but how about the carbon unstability? How will you explain? You already told that this is the order of stability, but we can see this is the opposite order, right? Here it was 3 degree was more stable, but here 3 degree less stable. Opposite order, stability order is opposite. The question is why and how will you explain? Anyone want to try? Very logical. Very logical. Okay, I'll give you some clue.
Oh, sorry. Does it have to do with like deficiency and like is it because it's like more rich, like the carbon's more rich this time?
Carbon is more rich, that's perfect, but again we can explain using that concept of inductive effect. So that means methyl group, inductive effect, inductive effect, inductive effect, inductive effect, inductive effect, right? So 3 degree carbanion, you have a 3 methyl group. So three of them pushing electron to carbon center, where are you negative charge. Now left hand side that carbanion, 2 of them pushing electron to this carbon, but here one guy. Now carbon anion, already carbon is electron rich, right? Carbon rich, unstable. Now again 3 of them pushing electron to the center. He become more unstable. Makes sense? Why 3 degree is more unstable than 2 degree? Because carbon already electron rich. Carbon here already electron rich, right? Now those methyl group CH3, CH3 and CH3, now they are pushing electron towards carbon center by plus I effect, inductive effect. Methyl always have plus I effect. So that means he is already electron rich. Again, those 3 guys giving electron to their carbon center, so he become more uncomfortable because he already rich person, so he don't need electrons, right? So that means, but if you compare this one with CH3 and hydrogen, now this is also carbanion, but here only 2 methyl group pushing electron. Now in comparison, both are having negative charge, but right hand side number 2, better than the number 1, because he has electronegative electron rich center, but 2 of them pushing electron, that's okay, but here 3 of them pushing, so the magnitude is higher here, that's why he become more unstable. Then 1 degree, CH3, negative charge, hydrogen, that's why you ordered in this way that 3 degree, so this is a 3 degree, this is a 2 degree, this is 1 degree carbon ion, and that's the stability order. So just opposite to carbocation stability, we know that carbocation stability, we know that carbon is 3 degree carbocation is more stable than 2 degree, but here carbon ion 1 degree is more stable than 2 degree, 2 degree is more stable than 3 degree carbon ion. Is it clear, everybody? Any questions, anybody?
That makes a lot of sense. It's pretty cool.
Thank you. Now, next, if we have dot 1 electron, what does it mean? And you have this one, what does it mean? And if you have hydrogen dot. Now, if you compare these three, what do you see? This is a 3 degree carbon radical, this is a 2 degree carbon radical, this is 1 degree carbon radical. I hope you guys understand that I'm representing this one is a methyl group, hydrogen. So 1 carbon, the carbon we are bearing electron, the like single electron, it's connected with the 1 carbon, that's why this is 1 degree, but here two carbon 2 degree, and this is degree. Now which one is more stable, which one is less stable? Can you order them? 1, 2, and 3. Increasing stability order. Okay, again increasing, EASING, increasing stability order. Which one is more stable and which one is less stable? Okay, here
would it be 3, 2, 1?
Increasing stability. So stability, 3 degree is more stable than 2 degree, 2 degree more stable than 1 degree. Same effect, you have to consider negative charge, plus I effect of methyl group. You have methyl group. So methyl group is very important for understanding or explaining stability of those kind of stuff. So this is just a simple example. I'm just trying to build up your concept. But if we have a different types of example, you have to apply that knowledge. Always make sure that you're following that strategy I'm giving you. That I'm giving you some very simplest example, and you get some idea, understanding, and not until you work on the problems, you're not able to get no confidence or 100% satisfaction. So that means, let's take example. If we have a molecule like this, or if you have a molecule, now here I have a positive charge over here, and I have positive charge over here. Now, which one is more stable?
Is it the one that's closer?
Is it the first one?
Yeah, the first one.
First one is more stable. That means what is our first target? Our first target is the carbon bearing positive charge. It connected to 1 carbon over here, 1 carbon over here, 1 carbon over here. That means this is a 3 degree carbocation. And the left one, the carbon bearing positive charge connected to the 1 carbon. That means this will be your 1 degree carbocation. So the stability order three greater than 1. Oh, I mean, sorry. I mean, 1 greater than 2. Right? Makes sense? Yeah. So 1 is more stable because it's a 3D carbocation. And now we explain why the reason of. So basically, they are a methyl group. Here also you can think about the same thing. They are pushing this electron density from bond pushing towards the electron deficient carbon. Okay, so all right. So think about that. Next lecture we'll discuss more examples, and then we'll move to the spectroscopy, IR and mass spectrometry. Because whatever we have covered so far, this is good for, enough for understanding reactions mechanism and chemical reactions on remaining chapters. So I repeat again, just for 1 minute. The first thing we have to know the bond. If we represent a molecule in a skeleton structure, you have to recognize that what kind of bonds are there, pi bond, sigma bond, how many hydrogens, carbon, nitrogen, oxygen, that you have to have confident. And also hybridization followed by resonance, very important resonance, curve arrow, and inductive effect, then electronegativity, and then isomers, and then acid base concepts. There are so many things, acid base concept. And now here today I explain carbocation, carbanion, radicals. This is, I mean, we have few things like steric factor, like it's called steric effect. So if you know that, that will help for stereochemistry. Steric effect. That's the one thing, basics. And if you have a few more things, we'll discuss later. Okay.
Hey, Professor.
So, yes.
Real quickly, could you draw a red arrow on figure 2?
Oh, okay, sure. Very good. Thank you for asking.
Dr.
Thank you.
May you explain why in the radical, why the 3 degree is more stable?
So, as I mentioned that something called octet rule. If outer orbital you have octet 8 electron, that is more stable, right? Now check about the how many electrons you have. 1, 2, 3, 4, 5, 6, 7 electron, correct? Agree?
Yes.
Now here you have, again, you have a 7 electron. Here you have a 7 electron. But if we have methyl group, that means it is pushing electron towards this direction, pushing electron towards this direction, this direction. That means electron density pushing towards carbon greater amount in 3 degree. That's why carbon become like try to minimize its electron deficiency. I mean, not electron deficiency. It try to get octet fill. So higher probability is here in 3 degree to get octet fulfill. I mean, not octet fulfill because electron is not here, but the effect of I, inductive effect, helps the carbon, okay, maybe try to get more electron density and carbon become in 3 degree more stabilized than 2 degree than 1 degree. Make sense?
Yes.
I mean, we are not able to count the electrons here, but the electron density movement of where you have more electron density towards. If you see methyl group pushing electron towards radical center, all right. Okay, so radical chemistry we don't have that much, but we have to understand carbocation and carbanion in details. Okay. Electrophile, nucleophile, very important. I repeat again. I have posted like 30 examples. So work on that. Ask me if you don't understand any of the examples. I'll explain again next lecture and we'll start spectroscopy. We don't have anything in chapter 1 and 2. Prepare for exam. I'll give model question paper. Thank you.
Thank you.
Thanks, Professor.
Thank you.
Yeah.
Thank you.
Have a good day.
Thank you.